Hello, I'm Ian McNerney, and today we'll be presenting work that Eric Kerrigan, George Constantidis, and myself from Imperial College London have done to design a closed-form preconditioner that we can use for linear predictive control. Some of the key features of the preconditioner that we're presenting today is that it is horizon independent, so we do not need to know the final horizon of our prediction problem when we're doing the design. We get comparable performance to existing design methods using semidefinite programs. The design computations that we do scale with the number of states and inputs, but do not scale versus the horizon length. To do this, we exploit the Toeplitz structure of the condensed Hessian matrix. However, this does lead to a condition where we can only use the preconditioner on systems that are sure stable, so that have their eigenvalues inside the unit circle. So in this talk, I'm going to first present some preliminaries on model predictive control and on preconditioning. Then I'll discuss some spectral properties that we've derived for the Hessian matrix of the condensed linear predictive control problem. Then I will describe the preconditioner that we're designing and also present some results on its spectrum of eigenvalues. So in this work, we're using the constrained linear quadratic regulator problem, where we're trying to minimize a penalty of the states and inputs. So we have the Q matrix weighting against the states and the R matrix weighting against the inputs and forming penalties. We also have a separate penalty matrix for the last step in our prediction horizon at step n. So we have a horizon of length n. We're constraining this optimization problem with the system dynamics xk plus 1 is equal to axk plus buk. And we are assuming that there are some sort of input constraints. This problem formation is the sparse form or the full form where we have both the states and inputs. We can then actually condense that down into a form where we remove the states and are left with only the inputs and optimization variable. And to do that, we need to form a new Hessian matrix. We call it HCP. And that is formed by looking at the prediction matrix. So we're going to essentially take this gamma matrix and we form the prediction matrix. So it's B on the diagonal, AB on the lower diagonal, A squared B, and so on down until the end of the horizon. That is multiplied against a Q bar and added onto R bar, where those matrices are just defined to be block diagonal with Q and R respectively. These matrices go in and form the condensed problem, where we now no longer have any equality constraints and we no longer have any state variables. It is simply the input variables in the problem. This means that it's easier to use first order methods in the primal domain, such as the fast gradient method, because we no longer have those equality constraints to have to try and project onto. We can now simply project onto a inequality set. When using these first order methods like the fast gradient method, their convergence rate depends on the conditioning of the optimization problem. In our case, that is going to be equivalent to the condition number of the Hessian matrix, HCP. And one method of trying to get better convergence rates, so converge faster, is to apply a preconditioner to the Hessian matrix. In MPC, that's commonly done as a symmetric preconditioner. So we're doing an ln inverse on each side and multiplying that in there. That way we preserve the symmetry of our Hessian matrix because HCP is symmetric by nature. So the pre and post conditioning for symmetric preconditioner preserves the symmetry of our Hessian matrix. Additionally, we usually choose L to be block diagonal. That way you don't end up with any sort of mixing between your different horizon steps. So your projection operation no longer has to take into account dependencies between each horizon point, is just at each horizon point. There are two existing strategies for doing preconditioning of these methods. The first is matrix equilibration, and the other more popular one is to actually form a semidefinite program to find the matrix L that minimizes the condition number of our resulting preconditioned matrix. If we look closer at the prediction matrix, we can see that it has what's called a Toeplitz structure, where each diagonal all the way down is the exact same value. So the main diagonal is B, the one below that is AB, and so on down the line. And when we're predicting a sure stable system, so when all the eigenvalues of A are inside the unit circle, this Toeplitz matrix can be represented with what's called its matrix symbol. To form this matrix symbol, we're going to just do the trigonometric polynomial, where the coefficients are the values on the diagonals. So it's the infinite summation of a to the I b times the complex number z to the negative I. This complex number z exists on the unit circle. This entire trigonometric polynomial is actually equivalent to a time-shifted version of our original system GS. So we can think of the matrix symbol for the Toeplitz matrix as being a time-shifted version of the transfer function of our original system. When we then look at the Hessian matrix, HCP, it also has the Toeplitz structure. This is because the Toeplitz structure of gamma is preserved across all these operations, and Q bar and R bar are Toeplitz by design. They have the same exact values on the diagonals. In this case, the fact that the Q bar matrix has a term P in the very lower corner doesn't actually matter for our design work, because a lot of the Toeplitz work goes into an infinite dimensional context, where we're essentially saying as the horizon n goes to infinity, so essentially we no longer actually have that last horizon step to wait with P. This means that we can then form a matrix symbol, PHCP, which is just going to be a combination of the matrix symbol for gamma and Q and R in the same exact form as HCP. So P gamma transpose times Q P gamma plus R. Now this matrix symbol allows us to find out values and find out properties of our full matrix by just doing some analysis of the symbol. So we can do some system theoretical analysis of the symbol. Two properties that we can use that with are the eigenvalues of the matrix and then the condition number of the matrix. So all the eigenvalues in the matrix HCP lie between the largest and smallest eigenvalues of the matrix symbol. That then means that the condition number, kappa, of the matrix will actually, as the horizon goes to infinity, be the same as the condition number of the matrix symbol. This is because the inequality of the lambda max for the matrix and then for the symbol is tight. As the horizon length goes to infinity, the eigenvalues will actually reach and be the same. We can see this on an example 4-state 2-input system. Our bound is represented by the dashed lines, so these are computed using the matrix symbol, and the circles are just with P equals Q, and the triangles are with the P is the solution to the Lyapunov equation. So as we can see, both of them converge to the computed bound in the matrix symbol. Now, when we talk about preconditioning, if we use a preconditioned matrix that is block diagonal with L on each component of the diagonal, we can actually see that the matrix HL, which is our preconditioned matrix, is also Toeplitz. And our new matrix symbol for this preconditioned matrix is simply L inverse times the matrix symbol for our original Hessian times L inverse transpose. This means that all of the original spectral bounds that we had on the previous slides can be extended to work with the preconditioned matrix, and we just look at the matrix symbol PHL and its eigenvalue spectrum to figure that out, instead of looking at the matrix symbol for PHCP. Now, because this is Toeplitz, we can also look into the Toeplitz literature, and we can see that there is a way of computing the preconditioner design that is actually going to be independent of the dimension of the matrix H. So this is going to be basically for the infinite dimensional horizon case. If we're doing a symmetric preconditioner, we then say that the blocks L inside that preconditioner are going to be the lower triangular Cholesky decomposition of the matrix M, where we define M to be B transpose times P times B plus R, and P is the solution to the Lyapunov equation. So all of the matrices in here are either going to be the cost function matrices or the system matrices, because this matrix P that we're using in M is also generally chosen as the final weighting term, so that matrix P in our cost function, for stability of the linear MPC problem. So in essence, we already have all the matrices for computing M for a stable, to make a stable MPC problem. And again, all of these are of just the small dimensions of either the states or the inputs. We don't have any dependence on the horizon length here. So let's look at how we design these preconditioners. To start with, we'll look at a semi-definite programming-based design flow. For there, we construct the optimal control problem, that constrained linear quadratic regulator. We then have to compute the entire Hessian matrix, H, that's of dimensions nm by nm, so horizon length times input. We compute the Cholesky decomposition of that Hessian matrix H. Then we're going to solve an SDP, and the matrices involved in that SDP are now of size 2nm by 2nm. So this is now growing with a coefficient of 2 in relation to the horizon and the inputs. We get the solution to that SDP, and then we compute the eigenvalue decomposition of a smaller set of that. So we end up with an nm by nm matrix we're computing the eigenvalue decomposition of. And using that eigenvalue decomposition, we then reconstruct the blocks of the preconditioner matrix by doing some inverses of the eigenvalues and multiplying again through by the eigenvectors. Now the design flow we're proposing is where we still construct the optimal control problem, but now instead of computing the entire Hessian matrix, we compute just the solution to the Lyapunov equation. So this is doing computations that are only in the dimensions of the states. This is also a computation that you could do if you wanted to have a stable linear MPC problem where you wanted that P weighting term at the end to guarantee stability. We then take the result from there, the P matrix, we put that into the expression, we end up with the M matrix, we compute the Cholesky decomposition of this, which is again Cholesky decomposition of only an M by M, so only on the dimensions of inputs. And then we invert the result, so we're inverting an M by M matrix to actually get the blocks of the preconditioner matrix. So we're no longer working with matrices that have dimensions that scale with the horizon length. Everything is in the dimensions of just the states and the inputs. When we look at the results and compare this against a semi-definite programming preconditioner, we can see that for this 4-state 2-input system, we get the same condition number for the resulting Hessian matrix as the semi-definite programming preconditioner. However, the SDP-based preconditioner had to be recomputed for each of these horizon lengths. So for each dot on this graph, we had to recompute an SDP and find that preconditioner. Whereas the one that we've proposed here uses the same M matrix across the entire horizon spectrum here. And all you're doing is you're just adding on another L block to make it so that you have the same number of blocks as you need for the horizon length. Now, if we look at how this scales and we look at the conditioning, we're going to now change the problem a little bit so we have a beta Q. So we're now saying that Q can vary a little bit and R is constant. In this case, we see that for a nicely conditioned problem, we have similar results for both lambda min and lambda max. But as some of these problems get more ill-conditioned, we do start to get differences in the lambda min and lambda max. However, this doesn't actually manifest as a difference in the final condition number. We still get the same condition number between an SDP method and the closed form method, even though we get the different minimum and maximum eigenvalues of the two methods. And that's because the SDP method is actually forcing the lowest eigenvalue to be 1, whereas our method allows it to be free. Additionally, after a certain point, these matrices become and make it difficult for the SDP to even be solved, so we end up with an infeasible SDP that can no longer be solved for some values of beta. However, the closed form method that we've proposed can still be solved in those regions. So we can still get a preconditioner in that region. So in this presentation, I've shown a closed form and horizon independent preconditioner. This preconditioner gives us equivalent performance to the semidefinite programming based preconditioners that are existing in the literature. Now, as I said though, this does rely on sure stability for finding that trigonometric polynomial of the Toeplitz matrix. So in the future, we hope to extend these results to work with non-sure stable systems and be able to get a closed form preconditioner for those. And then we're also looking at actually applying this preconditioner to some first order methods, such as the fast gradient method, to see their performance in practice. Because in this talk, we have only examined the resulting eigenvalues and condition number spectrum of the actual matrices, not how it's been applied to an algorithm. Thank you.